Okay, before breaks, we covered the formula to find the net force, to find the net force. And this formula again won't be given in the test or final exam, right? There's a constant value for E epsilon sub-zero, humidity of space. This value also won't be given. You are expected to memorize. This now is force. Right? The second equation for today is energy. Right? So as you can see on the screen here, there's a difference between this graph. This graph is force versus distance. Second graph is on the energy. Energy, energy versus distance. So back to the graph just now. The one on the top of the graph is positive force. The one on the bottom is negative force. If you get positive force, normally it will fall under attraction force. If you get negative value, you get under repulsive force. Energy also same, you have positive value region. So as you can see on the screen here, the energy start from 0. So 0, A naught means the stable distance or equilibrium distance. So let's say two element, not two element, but from the center to the stable element. Then you have attraction energy and repulsive energy. A big flip over compared to force. Force just now, attraction is on the top, repulsive is on the bottom, but when you flip to energy, attraction is at the below, repulsive at the top. So same, you have one new set of formula to calculate net energy. The front one, every time you see Z value is attraction force. And then the second component, B divided by A exponential N, that one is repulsive energy. This also won't be given in the test or final exam. What need to highlight here is the value here become positive compared to the previous one. Previous one is negative, negative, but when it comes to energy, the equation become positive, positive. Okay. So when you become positive and you input the Z value, when it become attraction energy, the front one will automatic negative value. So that's why on the graph here, you see attraction will be on the negative side on the graph. Okay. So the rest you read. And then there is a level or there is a condition where you will have a minimum energy at equilibrium. We call it E sub minimum. Is where you have the distance of A sub naught with a very stable distance. Okay, we look at example later. The rest you read, Rest you read. So on the left is force, on the right is energy. So how you link energy and force? Energy is a product of force and the distance of the electron, right, or the radius of electron. So you get integration of force dr. So what mean by force dr is the area under the graph. Right, you learn calculus when you have integration of a function, force versus distance. Force versus distance, you when you do integration means area under the graph, right? So the net force, you put in the limit from infinity to the radius of stable. Why it start from infinity? Because electron is free to move at infinity. You move from outside to inside. When you do calculation for electron, especially ionic bonding, you look from outside to inside. That's why your limit from infinity, distant infinity, to a stable A sub 0. From outside until the stable force. You cannot move inside further, because if you want to push this one inside, it's very hard. You need a very large energy to push this electron inside. Okay. Why? Because the positive charge inside is very strong also. Okay. So just now we learned the function, the equation for net force. Net force, you have two components, attraction and repulsion. So same, you break your force component into two, attraction and repulsive. Because you have two lines here, the blue line on the top and blue line on the bottom, you get the area under the graph on the top and area under the graph at the bottom, you get the net force. Okay. Energy also same. Okay, energy also same. Energy, just now we mentioned the net energy is attraction plus the repulsive energy. So by comparing the equation that you see on the screen, so to calculate the energy for attraction, you use integration of the first component here. To calculate the energy for repulsive, you use the second component here. Okay. Let's look at tutorial question. So this one is available in your tutorial question number 79. Okay, let's say you have two elements. So attractive force between magnesium and S. So ions at equivalent is so and so. So the force is given. Just now, what we learned in the previous session is that we can calculate the force. Force, we have two components, attractive and repulsive. So magnesium 2 positive and S2 negative. Before you move on, you look at the formula just now. You need to have the Z value, right? So you look at Mg 2 positive. What does it tell you? How one element become positive? How become positive? Give electron, right? So 2 positive give how many? 2. So Z is positive 2 for Mg. S, how become negative? Receive. So 2 negative means your Z, one of the Z value is -2. Then this one, it give you attractive force is this one. 1.49 10 power negative 9. You on the left hand side already give you one value already. In the equation, you have Z1, Z2, not equation, but from the question, you have your Z1 and Z2 value. He asks you to find respondent inter-ionic distance, the first section. Second one, something changed to the S component, S2 negative ion, have radius. This one, calculate the radius of Mg. Repulsive force between the two ions at this position. So we start with the first component. First component A. How to calculate the responding inter-ionic distance? So in this case, you have this equation just now. F net equal to the first component, second component. Again, negative value, negative sign in the equation. If you write positive, then I will look at your value of your Z. Okay, but this is the formula we use for this module. So make sure when you put in your assessment, write negative in the formula. Okay, again, each lecturer have their own formula or prefer. So I prefer use the original one, negative. Okay, so since we are given in this case, we are given the attractive force. So this side repulsive force is not given, right? So we can just, in this case, we just look at this component. Look at this component. It's not that we take away this one. It's just that we focus on attractive because attractive force is given. Okay, then you have this one, you rearrange. You rearrange this one, you change net is not net because this component is attractive energy. You change this force to FA, attractive, because this component is FA. Then you rearrange because you want to find what? Distance. So which one is distance? Is your A. So it's a linear equation. You rearrange, you get A sub 0 equal to square root minus Z1, Z2, E square divided by 4 pi epsilon 0 F attraction. Again, this one is attraction, not net. You are rearranging the first component of the force. Normally, students make mistakes when it do rearrangement of equation. Sometimes they forget the negative sign. Sometimes they forget the square. Yeah. These are the common mistake lah. Sometimes negative, and then sometimes they forget the square somehow. I don't know why. They forget when there's a square root. There's a square when they rearrange. You need to use a square root. Okay. Then you have this one. You have Z1, you have Z2, you have the E. E just now I didn't give you, right? So in this example, I'll give you the value. Okay, so I already explained Z1 is the first component in this scenario because I give you the first element first, mg. So your Z1 is the mg. It's a mg. So mg is 2 positive. Okay. Okay, correction for my explanation just now. Z is normally is positive negative lah, but in this case, I think I mess up the positive negative. You use the tutorial question, the answer for this tutorial. Means you look at the sign, you just you just copy the sign, but actually you get the same answer also. Okay. Right. So the Z, you get -2 and +2. And then the E value is 1.6 10 power -19 C. So this value also expect you to know. You write this value, you get extra point, 1 marks. Okay. Okay, so for Z1, Z2, we follow the definition that I write on the slide here. So it depends on number of electron. This one no issue. But I bracket, they must have a opposite sign. Means just now the explanation just now, you add in this definition, means you flip the sign. Or when you look at the question, you just copy the sign. The magnesium 2 plus, you just copy the plus 2. If you look at the element, you have 2 negative, means minus 2. You just copy the sign. Just to be consistent. So the epsilon 0 also same, constant value, 8 point something. Careless mistake normally is the minus sign, is the exponential minus, this one sometimes missing. Also this one also sometimes missing. So this some error. So you have most of the value here. You have Z1, Z2, E, epsilon, force you also have. So 4 pi, you know the value of pi. So in calculator, you press, you arrive at one answer. Okay. So you substitute. Again, there's some marks for the calculation. So the answer expected is 2.49. Again, for this module, minimum 2 decimal place, maximum 3 decimal place. Right? So you in the unit SI, meter. Okay. Okay, next. I will move into nanometer, because if you study about electron or atomic size, normally we use nanometer things, but you can hold your answer in 10 power negative 10, no issue. Okay, next look at number 2. B. If your S2 negative ion has radius so and so, calculate the ionic radius for magnesium 2 plus. So you just now you have the equilibrium distance, A sub naught. This one is equilibrium. What mean by equilibrium? Is the distance, let's say forum lithium on the screen here. The equilibrium, if you mix lithium and forum, this distance between the two center is A sub naught. Is it? Different answer. Okay. Okay. We come back to the answer first. I'll come back to the answer, but the concept is use this one. Okay. Then once you get the this one, then you use the value that you get just now. You calculate the R for first element, R for second element. So A not equal to R magnesium plus R as negative. So you given the S radius already, you have the value for A sub naught just now. So only have one missing information. You do the calculation. It's a subtraction. So you get R for magnesium equal to so and so. Okay. Right. The concept is this one. This A naught concept means it's a distance between the two elements. Okay. Now, repulsive force between the two ions at this position. Just now you calculate the attraction force. Now you calculate the repulsive force. You use the second component of the equation. So this is the second equation of the equation just now. So you have equilibrium. So your net force is 0. Then you have the attractive force. It should be positive here. Okay. Then you have the B and A. Okay. Do we have the B? The B. A not you have. And I jumped too fast already. This is working. Okay, I owe you the answer for this one. There's something missing in the slides. Okay, what answer you get for A? Do you guys get the answer? No. No. Okay, never mind. We move on. We come back to this one later. But you know the concept, right? Use the formula, then you apply. Okay, I still owe you one answer for this one, for the repulsive one. Okay, normally B will be given, the value will be given, right? Okay, let's look at example number 6. Same concept. So this is your tutorial question number 80. Repulsive force is given between the two elements, Na, this is NaCl. So NaCl, you know this one is ionic bonding, also primary bond for these two. So equilibrium is this one, repulsive force is given. Calculate value of constant B using repulsive force. This one is the working to calculate the B, and you need to find the bonding energy. Assume N equal to 9. Just now, I think the question, I didn't give you the N. So let's look at this one. So same, for the force equation, F net equal to so and so, attractive minus attractive plus the repulsive force. Okay, so same. Now you focus on repulsive, right? You're given repulsive, so you have this formula, and then you know that the hidden formula, which is the A naught. A naught is the radius between the Na and Cl. Okay, the radius, the equivalent radius is the radius Na plus radius of Cl. This one is a hidden formula. You should know, huh? Then the R is also given. R is given, so you just substitute the value for Na radius and Corida Cl, 0.181 nanometer. Then you get an A, the equivalent distance radius, 0.276 nanometer. So repulsive force is the second component of the formula. So you write F repulsive equal to minus NB divided by A superscript or exponential n plus 1. N value is given. So N is given 9. Repulsive force is given minus 3.02, 10 negative 9. To calculate the B. Again, rearrange equation. B expected is 8 point something. Power minus 100, 106. It's quite a big number. Hey. There's no 10 here, typo error. This is a reference number, reference number. You check whether this one correct or not. Okay. But the concept is, again, apply the formula, substitute the number. Okay. So far, we haven't do in differentiation, integration, just rearrange of a linear equation. Okay, once you get your B, again, a typo error, there's no 10 in the answer. So we want to find the bonding energy. So bonding energy, again, different formula already compared to the first one. First one is force, second one asks you about energy. So don't use the wrong equation. This is the way we trick you. I mean, we trap you in your answer. Because your brain, if you're not careful, you will do bonding, you will do an force here. Read carefully the question. So again, you have two components, attractive energy and repulsive energy. So you have the B from the first section. A, you calculate already. N, you calculate already. Z1, Z2, you know. You just copy the positive and negative. So one is 1, one is a -1. E, you memorize. E epsilon, you also memorize. Okay, substitute, you get one answer. The answer is -7 something, 10 power -19. Joule or Newton meter? Negative. I think it's positive. Positive. Okay. Yeah. Typo error in my this one. Positive. But still, why negative? Because one of it is negative. Because negative value here. And this one you get positive value, but still negative. Okay, just a reminder, Newton meter, your conversion is 1 Newton meter equal to Joule. Okay. Okay, I think for next lecture, okay, so for example 5, I need to go back to the textbook because for question example 5, I still owe you the unknown number, which is the the n number. N number I didn't give you. N number is missing. So the step here is that normally the question will give you the n. If this case come out in a test or exam, sometimes we forget to give you. You can assume. You just because you want to solve this one and the value is not there, you can in your answer you can write n value is not given. You can write assume n equal to any value you want. Cannot be 0 lah. You can put 1 or 2, 3, 4, and then you substitute, then you calculate. If this situation come in the assessment. Okay. Okay. Application of formula. Next one, we look at ionic arrangement. So this one is how the ionic solid, they arrange their ions. How we define the arrangement, we use one term called packing efficiency. How they pack, the number of cation, positive charge that can pack around an anion. We call packing efficiency. Affected by two factors, their size and charge neutrality. For example, the one you see on the screen here, the packing efficiency depends on the size of the electron and also the how many charge you have. Okay. The rest you can read. So the first one, for CSCl, the first type is in this form. So this is, we call it packing efficiency, is how the positive charge and negative charge, they can bond together. So CS, if you look at the periodic table, CS is row number 6, column number 1, period number 6, row number 1. So row number 1 means they have one positive charge. One electron, it contribute 1, so it become 1 positive. So CL is at group number 7, column 3, row number 3. So it will form, in this case, in this scenario, they give you 8 Cl surrounded by 8 Cl packed around a center C positive. So positive in the center, and then 8 Cl around the atoms. Okay. Later, when you talk about packing, you try to imagine you are holding a snooker ball. You try to pack a snooker ball, right? Okay. So this on the left hand side is CSCl. On the right hand side is an example of NaCl. Is how they pack. So in this case, on the diagram here, 6 Cl packed around a center Na inside. So how do you calculate the ratio of radius? Also, one question come out from will ask you about this one. Huh? So ratio, you take cation divided by anion, positive divided by negative. So you'll be given the radius of that element, you divide by the radius of negative element, right? It will tell you to calculate like ratio of radius of cation to anion. So you take positive charge divided by negative charge, radius. So in this case, you are given the radius of CS so and so, CL so and so, you just divide, you get one number. That is a packing number. So same for NaCl. You take the radius for Na divided by Cl negative, positive divided by negative, positive charge divided by negative charge, cation to anion. You get 0.5. So how do you read this ratio means? As the ratio decrease, there will be fewer anions surrounding the cation. So for example, this NaCl is 0.5. So 0.5, you have 6. 0.9, you have 8. So the less number, the less anion will be surrounding the things. Okay, so the lower packing means less neighbor that you have. Okay, so you need to understand the meaning of the value. Don't chase after the digit here. Right. So maybe the question asks you compare two products and ask you which one will have a fewer anions around the cation. I'll give you two numbers. One is, let's say, 0.9 and 0.5. Element A and element B. Which one have the fewer anions around the cation? So this is the slide, the application for that one. This one you read. So this one, again, example, we pull the Li and F. So this is the lithium fluoride, is how they form. Of course, we won't ask you to draw something like this, but at least you are exposed to how they arrange. Their ionic bonding. And from this ionic bonding, you'll be given the radius of barium, the radius of lithium, So ask you to find the ratio between the positive charge and negative charge. So the same question can come up from the previous example tutorial, just add in the section. Okay. Okay, so this one you can read lah. So to form the product of Li fluorine, it gives you the energy needed 617. So the formation heat is negative something, 600 something kilojoule. Be careful on the unit kilo, means 10 power 3. Yeah? So don't forget about the K in your calculation. So these are the 5 steps where how they form, how the bonding form. Okay. So I think this one you, okay. First, this one, Li, will change to gas. This one, when Li, this one, it will contribute 1 electron out. It become Li positive. It become ion. Okay, so okay, then for F also same. F also same. The rest you read lah. It's just removing electron, how many energy it have, and so on. Okay, so this one already explain why the 2s1 is there, because it's at the second row of the periodic table. There is a release and formation. Okay, this one is just steps lah. Read, there are 5 steps there. So introduce you to one law, is called His law. You just need to add the heat of formation between the element that involve. Sometimes 2, sometimes 3, sometimes 4 elements. So you just need to add the heat formation together according to Hess law. Okay. I'll give you one example later. This is just a illustration how the number works. So there will be, sometimes the table will be given. So as you can see, ionic solid, LiCl, NaCl, KCl, and so on. So how to read this table? You have lattice energy. One is in kilojoule, one is in calorie. Normally, we will use kilojoule mole. There's a conversion between these two rows. But you focus on this one. And then the melting temperature. Can you relate the lattice energy and the temperature? What happens if your lattice energy increase? What happens to the temperature? Melting temperature also increase. Meaning, if you have a very high lattice energy, also have a high melting point. You need high melting point to destroy the structure. Okay. So from the periodic table, what can you explain about the element? Lattice energy decrease as it's moving down in groups or as the size of ionic increase. So maybe this one is confusing. You read the first statement. Lattice energy decrease as move down in groups. So this is group number 1. So the energy decrease as it move down. Right? So for example, NaCl, these two, let's say the same Cl here, but as it moves down, the lattice energy decrease. As you can see, it dropped from 800 to 700 something. Just change the Li to Na. Where is Li? Group number, this one, row number 2 to row number 3, but still group number 1. As you move down, energy decrease. Okay, move down, energy decrease. And also, what happened if you move down here? What happened to the size of the ionic increase? If you move down, increase. Okay. Again, if you're not familiar with the size, go back to the previous session. We already explained how the size of ionic increase already. Okay. So this one, the value, all these are negative, huh? Just a highlight. Although you see positive value there. Okay. Second, lattice energy significantly increase when the ion involved have higher ionic charge. What I mean by higher ionic charge? It means it become 2 plus, 3 plus, 4 plus means higher ionic charge. So if you move from here to here, the energy will increase. Okay. So this one already explained how the lattice energy involve the melting temperature. This one you read lah. So ionic solid, they have all these properties lah. They have all these properties. They're hard, strong, rigid, brittle, and so on. This is how the ionic solid happen. Let's say you heat ionic solid. You can take example of NaCl, your salt, your salt. So if you hit with the hammer, external force, this one. So actually you are shifting the ion in this way. Then there will be a crystal crack happen. Okay, there's a shift of positioning when you have a ionic bonding. Hit, then it will shift, and then you will break. This one you read, So when you break, it's like a magnet. Your shift, you have positive, negative, positive, negative, positive, negative, positive. When you hit, let's say you hit until here, the molecule meet at here. Positive, positive will repel itself. Negative, negative will repel. Positive, positive repel. So you create a repulsive force. That's why it's very easy to break ionic bonding. Like salt, you easy to break because of this configuration. Because it shift down, then the charge meet together, it repel like a magnet. Okay. Okay, this one I go very fast. Covalent bonding. So covalent bonding, normally they are non-metals. Non-metal plus non-metal, like Cl square, like molecule of Cl. Cl or okay, or carbon dioxide. Normally they are the one that non-metal plus non-metal, the one that you see on the periodic table. So the example they see on the screen here, they are hydrogen. Again, hydrogen is a very special element. Okay, so this one is share. This one you learn in your chemistry already. So when you share, you will form molecule. So if you see this hydrogen, and you look at the potential energy and the separation distance, so you will have the equivalent distance just now, Na. So when you have equivalent distance, means two molecules will form together in an equilibrium. Then as you break them away, the energy will go from negative, then it will move towards positive. Okay, negative, it will break towards the positive. So this one you already learned in your chemistry. When you share one electron, you get one bonding. This one, single bond, double bond, triple bond. Okay, this one you learn in your chemistry already. And this is called Lewis's electron dot that we cover, that you've seen in the previous slides. So this one you read. So there are factors that affecting the bond energy. The atoms, electron configuration, the nuclear charges, which is the positive charge inside the nucleus, and the atomic radius. This one you read, got information on the screen, you can read. Okay, what we need to highlight here for covalent is that covalent bond, they have direction. Okay, they have direction. Ionic bond, they don't have direction, but for covalent, they have direction. This is information, extra information for you guys. So as you can see, there's a type of bond on the table: single bond, double bond, triple bond, and so on. So the bond energy, as it jump from single bond to double bond, almost jump one time, and triple bond almost triple the value of the single bond. Okay, and the bond length and so on. Okay, don't worry about the bond here because they won't ask you about this section, right? So the idea here for this slide is that you should understand when you increase the number of bonds, the bond energy will be increased. Okay. The rest you read, You should read. Okay, example for carbon iodine, ClI, and carbon bromide, and ClCl4, carbon chloride. This information for you guys. I won't ask you in test or fun exam. Okay, just information, right? So as you can see, the bond length increase as the diameter of the bond bonding with a C increase. This is you can see from the periodic table. The bond length increase as the diameter of the atom bonding with the C increase. So what does it mean? If you take these three colors, you combine with the carbon, the bonding length will be increased depending on the atom that you combine. Okay, so Cl, C and Br, C and Ci. So the diameter, the bond length, the longest one is I with carbon, then followed by Br, C, and Br, because of the radius of the element. Okay, so as you move lower, you see the length of bonding will increase as you move down. Okay. So one thing we interest is the bond energy. The shorter the distance between the two means the bond energy is higher. You need more energy to break these two as you move further, the distance between the elements. Okay, it's more easy to break this and this one compared to this and this one. Okay. As you read, Okay, this one also I'll go very fast. So just for your information. So we are in the covalent bonding. Covalent bonding is divided into non-polar and polar. So for non-polar, the sharing of bonding electron is equal. Then you call non-polar. Polar means direction of the attraction. So if the bonding is equal, then non-polar. So for example, H2, F2, and so on. Polar then means the sharing is equal. Sharing bonding between the electron is unequal. Then there is a direction of that one. So it will provide a polar covalent bonding. Okay, for example, this one. So H is balanced. But for example, hydrogen fluoride, you have a polar covalent bonding. You will see that F have more electron on this side, but this side is empty. So what happens if you have F and H, you copy the same molecule another side? Negative, negative, it will repel. If you have the same element, F and H, you copy this one, put here. When the F and F meet together, they will repel. So that's called a polar covalent bond. Means there's imbalance of, not imbalance, but there's a one side you have more electron exposed. Right? So let's say you know about how to write this electron configuration. So this one is C. C you have S and P. Right? Here you have one S, 2S, and 2P because it's on the P side. Okay. Then you will form other two lah. So here you have 4. 4 means you have a carbon plus carbon. You have 4 outside, then you will form another 4 with carbon, then it will stable. Okay, this one you read because I won't ask you. Carbon, one type of example of carbon is diamond. So this is a diamond shape. Again, I won't ask you in the test, just for information. There's a shape for diamond. Right? We won't go deep into this structure. Okay. But there's a term you should heard before for diamond. There's a tetrahedral covalent bonding that looks something like this. Okay, so it will form a pyramid structure. So when you cut a diamond, you see some edges, sub-edges like this because of the covalent bonding. Okay, hydrocarbon, also important for your coming test. But this one there was a specific chapter before under polymer. Okay, for under polymer. So this is between C and H. C and H, if you look at periodic table, it also fall on the right hand side of the periodic table. Although H is on the right hand side, on the top of the graph, H is on the top of the graph. So H actually is a very special element. So be careful on the H. The rest you read. Hydrocarbon, how they share the bonding. Okay, so this one you learn in your chemistry, right? So we represent one line with sharing of electron. So for example, CH, we have this sharing of electron. I think we stop here. We continue our class in tomorrow, right? Tomorrow we have class, so we continue tomorrow.